Video, I'm going to quickly talk about how to do arithmetic with complex numbers, such as how to add two complex numbers, subtract complex numbers, multiply, divide two complex numbers. This one is fairly easy. You may have seen this before, but let's say we have two complex numbers, z1, which is a1 plus j times b1, and z2 is a2 plus j times b2. And let's say that's the Cartesian representation for z. And let's say we also have the polar representation for z as r1 times e to the j theta 1. And let's say that z2 is r2 times e to the j theta 2. So how do you add two complex numbers? z1 plus z2, you would simply add the real parts and you would simply add their imaginary part. And so the real part of z1 plus z2 becomes a1 plus b1. I'm sorry, a1 plus a2, sorry. a1 plus a2 plus j times b1 plus b2. And in the same way, you can subtract z2 from z1 by simply subtracting the real parts and the imaginary parts. And so we can say z1 plus or minus z2 is a1 plus or minus a2 plus j times b1 plus or minus b2. And multiplying two complex numbers, how do you multiply z1 and z2 together? Well, we can use the Cartesian form and simply multiply these two complex numbers. And if you do that, you're going to get, and then you can collect the real parts together and the imaginary parts together. But notice what you're going to get a1 times a2 plus j times a1 times b2 plus j times b1 times a2 plus j times b1 times j times b2. Right? But j times j is the same as -1. So you get minus b1 times b2. So these two terms together form the real part of this. So the real part becomes a1 a2 minus b1 times b2 plus j times a1 b2 plus b1 times a2. Okay. However, it will be much easier for you to multiply two complex numbers using their polar representation. So if that's an option for you, I think you should certainly consider that, because that's going to be a lot easier. When you multiply z1 and z2 using their polar representations, you're going to get r1 times e to the j theta 1 times r2 times e to the j theta 2, which gives you r1 times r2 times e to the j theta 1 plus theta 2. So what this means is the magnitude of z1 times z2 is nothing but the product of r1 and r2, which is the magnitude of z1 times the magnitude of z2. Now the angle of z1 times z2 is the sum of the angles of z1 and z2. Okay? So it's a lot easier to multiply complex numbers using their polar forms. The same thing is going to be true if you try to divide two complex numbers. Now, let's try to make some space here and talk about how to divide two complex numbers. Dividing two complex numbers is quite painful if you do them directly in their Cartesian form. I mean, it's doable, and you probably have done arithmetic with complex numbers before, So if we want to divide z1 by z2, then we have, in Cartesian form, we have a1 plus j times b1 divided by a2 plus j times b2, right? And if I want to write the result of z1 over z2 in Cartesian form, which means I want to write it as a real part plus j times the imaginary part, then it's not obvious how to get the real part and the imaginary part from this. And the standard, or one way to do this, is to multiply the numerator and denominator by the complex conjugate of z2. And the product of these two, if you try to multiply them out, you will see that this becomes just the square of the magnitude of z, or this becomes a squared plus b squared. Particularly, the imaginary terms cancel out. So notice that you get a j times b2 times a2 from here, you get a negative j times b2 times a2 from here, and so they both cancel out, and you get a squared plus b squared. And the nice part is that this is strictly a real number, right? So in the numerator, you're going to get the product of these two. So you're going to get a1 times a2 plus b1 times b2, and you're going to get plus j times b1 a2 minus a2 b1. But dividing this complex number by the real number is pretty easy, because you just divide the real part by this real number and the imaginary part by this real number. So the answer then simply becomes a1 a2 plus b1 b2 divided by a2 squared plus b2 squared plus j times okay. Now again, I would try to avoid doing this kind of lengthy calculations if at all possible. And one way you can avoid it is to think of the polar representations for z1 and z2. Now, the polar representation for z1 tells you that z1 can be written as r1 times e to the j theta 1, and z2 can be written as r2 times e to the j theta 2. Then z1 over z2 is simply r1 times e to the j theta 1 over r2 times e to the j theta 2, and this is r1 over r2 times e to the j theta 1 minus theta 2. So here is where you really are using the power of Euler's formula and the polar representation. You can see that this is just so much simpler to do, and notice that these e to the j theta 1s and e to the j theta 2, they follow exactly the same arithmetic as e raised to some real numbers, right? So it's e to the j times theta 1 minus theta 2. It becomes or the phase becomes theta 1 minus theta 2, the angle becomes theta 1 minus theta 2, and the magnitude becomes r1 over r2. So the magnitude of z1 over z2 is the same as the magnitude of z1 divided by the magnitude of z2, which is r1 over r2. And the angle of z1 over z2 is theta 1 minus theta 2.